Okay. Hi, everyone. I'm Chad. I'm a PhD student at Imperial College in London, although I actually did my undergrad and master's right here on the other side of the mountain at McGill, and spent a decent part of my childhood maybe like 200 meters away from here. Uh, so I'll try and be relatively quick so that we can maybe catch back up on the schedule a bit. But yeah, so today I'll be talking about this package we wrote called LoReSIO.jl, and it's package for local reduction for semi-infinite optimization. So I'll talk about what semi-infinite optimization is in a second, but I'll just very briefly talk about the kind of things that motivate us in doing this, where I work on robust control in general, and so we try and solve this kind of problem where you're trying to find a minimum over any kind of control gains, estimator parameters, or any possible design variables over the worst case scenarios of any uncertainties affecting your system. So disturbances, measurement noise, or just any parameters you don't really know the true values for. And then, like for any control problem, you're like subject to your system dynamics and any constraints you want to satisfy. But because we also look at measurement uncertainty, we also have like some measurement models we use. Yeah, so what's a semi-infinite program? So semi-infinite program is an optimization problem where you're minimizing some function where you're choosing a finite set of variables. So you're just choosing however many variables you have control of, but then you need to satisfy an infinite number of constraints. So you're satisfying some function like this g of x, y there for every possible value of y in a continuous set. And because these functions are nonlinear, that means that every possible point in this continuous set can matter, so you've got an uncountably large number of constraints. I'm also going to point out that this is another way of writing a nonlinear min-max problem, where you can just change to the subgraph or epigraph form or whatever you want to call it, and this min-max can become a min such that, so a min of an upper bound such that this your objective function is smaller than this upper bound for all possible values of your uncertainty. Why do we solve these problems? Well, it's useful for any form of robust optimization, but again, we're more interested in the robust control case, where in a lot of problems, you've got some uncertainties that are known and bounded. So it's nice to represent everything with like Gaussian distributions and all of that. But in a lot of applications, especially like the aerospace systems we're interested in, you just have some manufacturer spec that says the thrust you'll produce will be this value plus or minus 5% or something like this. So you've actually got known bounds on your uncertainties. And then, again, in a lot of cases, you want to satisfy some constraints no matter what these uncertainties are. Like if you're trying to land a plane, yeah, you want to save fuel and get there as fast as possible, but there are some constraints you really do not want to violate no matter what happens. Like you probably don't want to crash into the ground. And then another application we've been looking at is for lunar landers, where if you want to try and like plan something to land on the moon, yeah, you want to save fuel, but you also just don't want to crash into the surface. Yeah, so there are a few methods of solving semi-infinite programs. You can use any kind of global solver and then just treat your uncertainty as like an additional dimension. The problem is, for some of the problems we're looking at, we've got thousands of dimensions, and I've been able to use global solvers for like 15, 16-dimensional problems sometimes, but it's going to scale pretty poorly for problems this large. You can use any kind of random sampling if you want, but then it's really hard to get guarantees for any form of robustness. Or you can use something like scenario trees, which are probably one of the most popular approaches for this. But again, scenario trees, as you go and like predict farther into the future, grow very, very big, and so you've got these huge numbers of scenarios you have to handle. And then if you do like a more or less standard scenario sampling, where you pick the like middle and like two extremes of your uncertainty, if you've got some arbitrary nonlinear function, you're not actually guaranteed to capture the worst case scenario. So what we actually use to solve these problems is this method known as local reduction. It's proposed actually in the 1970s by Blankenship and Falk, where the idea there is that you iteratively solve a maximization problem to find, so given your current best guess for your the variables you're trying to minimize over, you find the worst possible realization of your uncertainties, add that to your scenario set, and then resolve your minimization problem for all of the past scenarios you've added. So the idea there is that you can then keep doing that until you can't find any scenarios that violate your constraints, which mean that you do not have any violations. And then the advantage of that is, again, like compared to a scenario tree, you just get way fewer scenarios because you only get the ones that are relevant or like active. And then you will always capture the like true maximum of your cost. So yeah, our package tries to implement this in Julia. We do a bit more than solving just general semi-infinite programs. We do handle equality constraints, which wouldn't usually be part of what you'd consider a standard semi-infinite program, and we kind of show how these can still be reformulated into a more standard approach and why you can still use local reduction to solve that. So we allow any u variables, which is what we call anything you can minimize over. Your w is your uncertainties. Then z is any variable that has to evolve uniquely. So in a control scenario, it's probably like your state or anything like this. And then s is any variable that needs to exist but does not need or necessarily have a unique solution. And then, yeah, so we don't define our problem directly using JuMP as a user input. We thought about trying to do that for a while, but it got very, very complicated. So instead, so that's kind of like stripped down code where I just left the bare minimum for people to understand what's going on. But the idea there is we allow for people to define different domains of the variables, and then different types of constraints. And then, so you could, for example, define a parameter, which is some variable domain that just does not change over time. Or you could define some other domain for a variable that changes over time, or things like this. And you can define, again, constraints that have uncertainties in them, constraints that do not, or even have another semi-infinite program as a constraint, if that's something you want to do. And then after the user defines all that, what we do is we take all of these definitions, build a problem description out of that, combine this with whatever method we want to use for the scenario selection. So you could, again, use scenario trees or anything like that. We do support that kind of thing. Or you could use local reduction, or you could just implement your own by creating your own scenario method type and just adding the relevant functions for that. And then we then transcribe this like user-defined function with the specific scenario method into JuMP, a series of JuMP models with different minimization and maximization models. And then we just, again, let the user define a solution method on how you want to alternate between solving these min and max problems. And then, yeah, distributedly solve these JuMP models until you converge to a solution. So that actually probably would not have been possible to write a year ago without the new nonlinear interface. It also makes very heavy use of the parameters people talked about earlier because, yeah, the max problems are very similar every time, but then you're changing a few things like the output of your min problem basically every time you're solving them. Yeah, so maybe some very quick things we've like solved with that. So that's a very simple problem just to show which you can kind of solve. So very linear dynamics. You just have your state that's evolving with some control input you can choose, and then some linearly added uncertainty. Your objective is just to get to some final goal at the end and minimize the total control input you use. And then you've got a very, very nonlinear, non-convex constraint, which is you've got to stay outside of the cylinder, and we do that by just saying you need to be out of the circle, or you need to be above the cylinder, or you need to be below the cylinder. So you've got two ors and a non-convex inequality. And yeah, we just throw that into our solver, and it'll give you a trajectory that no matter what value you have for uncertainty, you'll like never actually collide with the cylinder. We also looked at a simple 2D quadrotor problem where you are doing actually output feedback directly on your sensor measurements on this little quadrotor, where you actually don't really know what your mass is. There's a lot of uncertainty on that. You don't know your moment of inertia. Your measurements are highly noisy, and you don't actually know how much thrust you're producing exactly when you're doing that. If you try and like solve for like the optimal open loop performance, you get these trajectories that are trying to get this green thing, but end up all over the place. But then if we just find like 50 scenarios and just terminate our optimization early, so that we can design a controlled policy that gets there, you actually can see that even in the worst case, you still are flying, and then you're not too far off from the green target. Yeah, that's basically everything. So a few references here on the original local reduction method, and then some papers from our group on how we implement this to modern control problems. Yeah, that's it for me. Thanks.